Right. Good morning. So we're going to pick up where we left off yesterday. It was brought to my attention we don't have class on Tuesday of next week. So just so you know, I did move that homework assignment that was due Tuesday to Wednesday of next week instead. And we will not have class tomorrow, Monday, or Tuesday. Okay, so you get a nice long 5-day weekend there to maybe get some rest, get caught up on some things. But let me know if you have any questions over that break. I'm definitely working tomorrow and Tuesday. Monday, I'm planning to take a day just to kind of relax a little bit. But Tuesday and Friday, for sure, I will be working. Okay, so if you need to set up a meeting with me, or if you've got questions on homework or anything, please do let me know. Any questions about anything right now? All right. So back in the logarithm section, this is still 4.3. So I've got one more example I want to do here, and then we'll move on to the next section. Okay, so I want to find the domain of this function here. We have the natural log of 4 minus x squared. Okay, so what we have to think about is what do we know about logarithmic functions in general, and then how can we use that to help us find what this specific domain is going to be. So think about the domain of your basic log functions that we've looked at so far, right? And what do we know about the domain of a log function in general? Okay, so it has a vertical asymptote, right? And if it's just a base log function, where is that vertical asymptote? At 0, right? At y equals 0. So in general, we know that the stuff inside the logarithm has to be positive, right? Because all of our graphs, if it's just a basic log, base 2, base 10, natural log even, right? Doesn't really matter. The stuff inside there, the x value is always going to be a positive value. Well, now we've got more than just an x inside here. But we know our basic log functions, right? All of them, it doesn't matter what the base is, the stuff inside that logarithm is always greater than 0. So that's exactly what we're going to do here to figure out the domain of this function is we're going to take everything inside the log and we're going to say that it has to be a positive value. So I'm going to say 4 minus x squared has to be greater than 0. So whenever you're looking for the domain of a log function, right, it could be a natural log, a common log, a base 2 log, it doesn't matter. The stuff inside the log always has to be positive, so you can always take it and set it greater than 0. Now, if I want to solve that, what would I need to do? Okay, so you could subtract the 4. Okay, now remember in this case, because we have an inequality here and it's quadratic, what else could we do here to solve this one? We could, right? Because in this case, we do have a difference of squares, so this thing is going to factor. What would be the factors that would give us 4 minus x squared? Okay, so close. In this case, though, because the 4 comes first, what would you actually want to start with? Okay, so we're going to say 2 minus x is one of our factors. And because it's a difference of squares, what's the other factor going to be? Good, 2 plus. Okay. So since we have a difference of squares, first step is going to be to factor that. We're going to get 2 minus x times 2 plus x, still greater than 0. Now, once we've got our factors, now what can we do? Set them equal to 0. Good. 2 minus x equals 0. I've got 2 plus x equals 0. And now at this point, I need to solve each of these for x. So what are we going to get for this first equation when we solve it? Okay, so x equals positive 2. What are we going to get for the other equation? Good, x equals negative 2. Once we have those values, since we have an inequality, right, we're not looking for what x is equal to here, right? We want to know where this thing is greater than 0. So what are we going to have to do with those values now? So if we just plug those values in, right, keep in mind, we set the factors equal to 0. Plugging this in is just going to give us 0. Plugging this in is just going to give us 0, right? So that's not going to really help us here because we know that's just going to make this equal 0. If we want to know where it's greater than 0 instead, what are we going to have to do? Okay, good. So we need our number line, right? Or we could do a table of values with the intervals, but I'm going to do this on a number line here. And then we're going to pick some test points because we want to know where is it positive, where is it negative, and that's going to tell us where it's greater than 0. So keep in mind, right, the stuff we did all the way back in chapter 1, and then we redid it again in chapter 3. We're using it again. Anytime you've got a quadratic inequality like this, you're going to factor, you're going to find those zeros, you're going to put them on a number line, you're going to test each interval to see where it's positive and negative. Now, what's a value that we could choose down here to the left of negative 2? Negative 3 works. Now, if I plug in negative 3, I'm just going to plug it into this factored form right here to see if it's positive or negative. Well, 2 minus a negative 3, this factor is going to be what? Positive or negative? Positive. Good. 2 plus negative 3 is going to give us what? A negative. What's a positive times a negative? Negative. So everything in this interval down here now should be negative. What's the value between negative 2 and 2? It works. If I plug in 0 here, 2 minus 0, positive or negative? Positive. 2 plus 0 is going to be positive. Positive times positive is positive. Good. So everything in this interval here should be a positive. And finally, we need something that's bigger than 2. So what can we use? 3 works. 2 minus 3 is going to give us what kind of value? Negative. 2 plus 3 is going to give us a positive. A negative times a positive is negative. So everything over here now is going to be a negative. Now, which values do we care about? Positives, right? Because we want this thing to be greater than 0. That means we're looking for the positive values. That means all I care about is that one interval right there where we got positive values. Good, Kenneth. So it's going to be everything between negative 2 and 2. Now, the only question is, are we including those endpoints or not, right? So when we do our interval notation, what is it going to look like? We're not including them, so we're going to have to use what? Good. So it's going to be parentheses, negative 2 to positive 2, parentheses. So that's going to be our domain for this one now, right? Because those are the values that are going to give us positives inside that natural log. And so everything between negative 2 and 2, not including the endpoints there, that's going to be our domain. Any questions on the work there? Now, the nice part about these is we can look at the graph just to make sure that our domain makes sense. I'm going to go to the graph now and put this in Desmos. Get natural log 4 minus x squared. Let me share this with you. Okay, so there's our graph there, right? And we said the domain should be everything between -2 and 2, but not including those values, right? And if you look at this graph here now, it looks like there's a vertical asymptote at -2, there's a vertical asymptote at +2, and our graph is just everything values, which is why we just get the domain of -2 to 2. Okay, so always look at the graph, right, just to kind of double check yourself. Right? But if you've done the algebra correctly, it should be correct anyway. Any questions on that one now? All right. Section 4.4 now, so laws of logarithms. And so this section is the last one that's on the upcoming homework, right? So I think hopefully we'll get through enough of it today that you can do all the homework. So if not, though, we'll finish up on Wednesday for sure. So I think having that due on Wednesday night is still going to be okay, because I think we'll get through, like I said, most of this, if not all of it. All right. So here are our laws of logarithms. So our first one here, so first off, we're going to let a be a positive number, right, like we have for all of our logarithms so far. A can't be equal to 1, because if you have a base 1 log, that's going to be boring, because 1 to any power is going to be 1. We're going to let A, B, and C in this case, so all of these values here, sorry, this one down here, I need to correct, because I don't have the right one. Let me go ahead and write that in here. Go. All right, so A, B, and C, right? So these A, B, C values here are going to be all real numbers, okay? So we can put any real number we want to in there. A needs to be positive and B needs to be positive, though, right? So we can't have negatives inside of our logarithm, which is why we're restricting A and B to be positive values. Now, if all those things are true, then we can start applying these rules or these laws of logarithms. So if I have multiplication inside of a logarithm like this, and again, it's any base, it does not matter what that base is, then I can split this log up and do the base A log of big A plus the base A log of big B. So basically, multiplication inside of a logarithm splits into logarithms using addition now. So multiplication becomes addition when I split those logarithms. If I have division inside of a logarithm instead, now when I split that up, it's just going to become subtraction. Okay, so we're going to end up with a base A log of A minus the base A log of B. And so that's what we can do if we're expanding this out or splitting this into multiple logs. And then our final law of logarithms says that if we have an exponent inside of a logarithm, we're actually allowed to bring that to the front of the log, right, and basically drop it from the exponent. So then it becomes C times the base A log of big A here. So anytime there's an exponent, bring it out front, and that's what we're going to end up with there. Does anybody want more time to get those laws? All right. So again, they're in the slides, right? So if you ever need to look back at them, right, if you didn't get them in your notes, that's fine. So let's take a look at these examples now. So we want to evaluate each of these expressions, and we're going to use our laws of logarithms to help us do that. All right, so if we look at the first one here, we have a base 4 log of 2 plus the base 4 log of 32. Now, in that current form, it's going to be difficult, let's say, to figure out what the base 4 log of 2 is or what the base 4 log of 32 is, right? Base 4 log of 2 is not bad. We could probably do that one by hand. But base 4 log of 32 is going to be a lot trickier. So what I want to do first here is combine these logarithms into a single logarithm using those laws that we just looked at. Well, if I have addition here and I want to put these two together, what am I going to end up doing with the values? Good, Kent, right? We're going to multiply the two values inside. So this could become the base 4 log of 2 times 32 now. So because we had addition, as long as the bases are the same, we can combine those into a single logarithm. We just have to make sure we multiply what's inside now. Well, if I simplify that, what's 2 times 32 going to give us? Good. So we get the base 4 log of 64. And so now we just have to think, well, 4 to what power will give us 64? Good. So 4 to the 3rd power is 64. Therefore, if we evaluate that logarithm now, the answer is just going to be 3. Any questions on how I did any of those steps? All right, let's look at the second one now. So since we have a base 2 log of 80 and a base 2 log of 5, again, I can't figure out those individually, so I want to try to combine them and see if maybe simplifying it will actually help us to solve it. Good, so now this has come division this time when we put them together. So we're going to have the base 2 log of 80 divided by 5. So just make sure when you do your division, it's always going to be the first value divided by the second value, so 80 divided by 5. Now, if I simplify 80 divided by 5, we're going to have the base 2 log of what? Good, 16. So now we just need to know, well, 2 to what power will give us 16? 4. Perfect. So our final answer this time is just going to be 4. Any questions on that one? All right, now the last one here, we have a value out front, but using the laws of logarithms, what did we say we could do with that? Think in the actual laws, right, it was going the other direction, right? We started with an exponent and we were able to bring that to the front. So at this point, we have a value out front, right? We can move it into the exponent. So that's just going to become log of 8 to the negative 1/3. Good. Okay. That's all right, German. I know if you put certain parentheses and stuff in there, it automatically does the smiley faces, so no worries. All right, so now that we've got this, okay, let's see if we simplify what's inside this log now. So what could we do with 8 to the negative 1/3? So what can we do with negative exponents in general? Good. So we could rewrite that as a fraction, move it to the denominator. So this is going to become 1 over 8 to the positive 1/3 instead. Now, what does 8 to the 1/3 power mean? How can I rewrite that? So how can we rewrite fractional exponents? What if that was a 1/2 power? What's raising something to the 1/2 power the same thing as doing? Square root, right? So if this is a 1/3 power instead, what do you think that means? It's a cube root instead, right? So we can change this now to the log of 1 over the cubed root of 8. Well, what is the cubed root of 8? 2, right? So this becomes log of 1/2. Now, what's the base of this log? 10. Good. This is a common log, right? And we said the common log has an understood base of 10. So the question is, can we figure out something 10 to what power will give us 1/2? And I'm not going to waste our time. We can't do that by hand, right? So we can't just say, well, 10 to some power gives us 1/2. There's no nice value that's going to work there. So at this point, right, we could either stop there, that's an exact value, or if you have a decimal approximation of this, we have a common log key on our calculator, so we can just go in there and do the log of 1/2. So what would that give us? We'll just do 3 decimal places is fine. So log of 1/2. Good. So negative 0.301, if we round it off, that would be our answer there. Any questions on that one? Now, technically on this one, because we're going to end up getting a decimal value anyway, you could have just put this whole thing in the calculator to begin with, because you can put negative 1/3 log of 8. That should give us exactly the same decimal that we got down here, right? So I did definitely want to practice moving that to the exponent, simplifying that, because sometimes, right, if this had been a base 2 log instead, then we could get a nice exact value out of that. Right? But in this case, because it was a base 10 log, we can't do anything with that. So putting this in and putting that in should give us exactly the same decimal value. Any questions on that one now? All right. So now we want to extend, right? So we're given some logarithms, okay, a single logarithm. We want to expand it into multiple logarithms using the laws that we've got. So we've got a base 2 log of 6x. And so what operation are we going to have to use to expand that first one then? Addition, right? So now I have a base 2 log of 6 plus the base 2 log of x. Now, if you can simplify your log, do that. If it's not a nice one, right, if it's going to give you a decimal anyway, then just leave it alone. There is nothing that we can raise 2 to get 6, right? And so in this case, I would just leave that log alone. We've expanded it using addition. That's going to be our final answer this time. Key things here, though, the multiplication becomes addition, and make sure you keep the same base on both of those logs when you do that expansion. Any questions on that one? All right. If we look at the second one now, what's the first thing we're going to want to do with this? Okay, so overall, right, we're expanding, right? But to do the expansion, right, what's our first step going to be? Okay, good. So it's going to be the same property as before, right? Because like we had here, we had multiplication. We have multiplication here also, so we can expand it using addition. We're going to have the base 5 log. I'm going to take my x cubed plus, again, keep the same base. So base 5 log again. And then we have the y to the 6th power. So because we have multiplication in there, when we expand it this time, we're going to have addition in between the two logs. Keep the same base for both your logs. Now, do we have any other laws that we can still apply to that one to expand it even further? The exponents, right? Okay, so remember that third law of logarithms said that if we have an exponent, we can move that out front. So when I do that now, this 3 goes to the front of this log. So that's going to become 3 times the log base 5 of x plus, and now this one has a 6 in the exponent, so that 6 is going to come out front. So we're going to get 6 base 5 log of y. And then again, you would always look, do you have any other multiplication, any division, or any exponents inside of your log? And as long as you don't, then we know we've expanded it completely, right? So here we just x inside that log, no multiplication, division, or exponents. Here we just have the y, no multiplication, division, or exponents. We know that's fully expanded now. Any questions on that one? All right, so let's take a look at this last one here. So we got natural log a times b divided by the cube root of c. All right, so what do you think we want to do first here? Okay, so there is going to be some subtraction in there, right? Because we've got this division. What other operation are we going to have this time, though? There's also going to be addition because in the numerator, we've got multiplication, right? So we're going to actually have both pieces here. So what I'm going to do is I'm going to say, well, if we split this up, we've got an A, a B, and a C here, right? So we're actually going to have three different logarithms once we split it up. I'm going to start with the natural log of A. And because we've got this multiplication here, I'm going to have plus natural log of B. And now the division is going to become subtraction, natural log cube root of C. You can always go back and just make sure, right? If I were to put this back together, would it make sense? Well, this addition is going to become multiplication. That gives me the A times B in the numerator, and the subtraction becomes division, so I'm dividing by the cube root of C now. Now, the question is, have we fully expanded this, right? So we want to look at each of our logs and make sure we don't have anything else in there that we could do. Well, the A here, there's no multiplication, division, or exponents. That's good. The B here, no multiplication, division, or exponents. That one's fine. Do anything with this one, though. Okay, the cubed root, right? What could we do with the cubed root to apply one of our laws of logarithms? Good. It would become C to the 1/3 power, right? So now we're going to have natural log A plus natural log B minus natural log of C to the 1/3, because C to the 1/3 is the same thing as the cube root. Well, now that we've got an exponent in here, what can we do with it? Move it to the front. Good. So I'm going to move this 1/3 to the front of just this logarithm, right? Not to the front of the whole thing, just the front of that one. So this is going to be natural log of A plus natural log of B minus 1/3 natural log C. And again, we just go through, make sure there's nothing else we can do. We already checked the A and the B, those are fine. Now there's just a C here, so no multiplication, no division, no exponents. That now is fully expanded. Any questions on that one now? Okay. All right, so we're going to use those laws again here. Think about what we could do to actually combine these into a single logarithm. All right, so looking at that first one, what's the first thing we're probably going to want to do if we're trying to get all this together as a single logarithm? Good. So let's take this 3 that's out front here. Let's move it up into the exponent. So that's going to be our first step. So we're going to have the log x to the third plus. Now, same thing here, right? We have this 1/2 out front. So I'm going to move it up into the exponent of this one. So that's going to give me the log x plus 1 to the 1/2 power. Now what can we do? Good. So since we have addition here, we have the same base on both of our logarithms. I'm going to put them together into a single log using multiplication. So that's going to give me x cubed. And in this case, what's another way we could write this x plus 1 to the 1/2 power? Good. It's a square root, right? So this is going to become the square root of x plus 1. Okay, but notice here we're multiplying those together because we had addition here. Now we've got this all as a single logarithm. We've got our multiplication in there. We have no more exponents to move up, right? So that is our final answer as a single logarithm. Just in terms of the order that we do things, always deal with those exponents first, right? Move those up and then take care of any multiplication or division. Because otherwise, if we had tried to put this together before we did the exponents, because especially they have 2 different exponents, that's not going to work out. So move the exponents first, then combine using multiplication or division. Questions on that one? All right, so what are we going to do first with this next one? Okay, good. So we can move this 3, right, because that's going to move to the exponent. So that's going to give us natural log s to the 3rd power. What's next? Good. So we're going to get plus natural log of t, move the 1/2 to the exponent. And then finally, we're going to have minus natural log. This whole thing here is going to get raised to that 4th power. Okay, so just make sure when you put this in here, it's going to be t squared plus 1. And the 4th power goes on the outside of that set of parentheses. All right, so we took care of moving everything to exponents. Now what? Okay, good. So we have this addition here, so we can combine those using multiplication. That's going to give us natural log. Now notice here, right, we've got all natural logs, so we're going to be able to put all of them together. So we know these are going to become multiplication. This one, though, is going to become what? Division, right? So I'm going to multiply these 2 things, and then I'm going to divide by this one. So I'm going to put s cubed t to the 1/2 over, and then I'm going to put all of this t squared plus 1 to the 4th in the denominator this time. Right? So I'm multiplying these, dividing by this one. That takes care of the addition and the subtraction this time. Now, the only other thing we could do here, if you really wanted, we could change that into a square root. So if you want to rewrite that as natural log s cubed times the square root of t over t squared plus 1 to the fourth. You do not need to expand out the t squared to the fourth. Okay, you can just leave it like that, because otherwise you have to do t squared plus 1 times itself 4 times and multiply that. Just leave it in factored form like that. Any questions on that one? All right. All right, so if a task is learned at a performance level P sub 0, so that's basically the initial amount of material we learned, then after a time interval T, the performance level P, which is this value here, satisfies this equation. So basically what this is saying is we forget stuff, right? So if I were to take a test right after learning it, I'm probably going to do better than if I wait a certain period of time without actually reviewing the material and then try to take that same test again. Right? So P sub 0 is basically what did I get the first time I took the test. T is how long I've waited, and then all of a sudden we're going to take the test again and say, oh yeah, that's my new performance level now. Okay, that's what P represents. So what this is saying is, if your score on a history test was a 90, what score would you expect to get on a similar test if you waited 2 months, right? And so we're going to assume in this case that T is in months. That's our time. So the first thing we want to do here is solve for P, and then we're going to use this information to figure out what would our new score actually be if we were to wait, okay? How could we solve that first equation for P? That's the question. So what could we do first if you think we're going to try to get P by itself? Okay, so German, you're on the right track, right? So we could take the inverse of the log. It's a base 10 log. So you could raise everything to from the 10th, right? The base would be 10. So you could do 10 to that power. The problem is if I do that, I've still got a lot of stuff over here that I can clean up first. So I would want to do that even before I do what you just said. So what can I do with all of this first? Okay, good. So we have subtraction. We have the same base on both of our logs here, so that is going to become division. Is there something else we would need to do first, though? Move the C, right? Because we've got a number out front here, we need to move that into the exponent before we do that division. So let's do that. So I'm going to have the log of P equals log P sub 0 minus log T plus 1 to the C power now. So just remember, the first step is always to move any exponents that you can. Since we have a C out front here, we can move that into the exponent. That's going to give us this. Now, because we have the subtraction, now we can divide. So I'm going to combine two logs into a single log. That's going to give us the log of P sub 0 divided by T plus 1 to the C power. Now, once we've done that and we've got everything in terms of a single log on the right-hand side, what do you think we can do now? So subtract a log. So Asbel, are you saying move like one of these to the other side, like get them together? Okay, so if we did that, the problem there is then I would still have subtraction of logs. I'd have to then combine them. I'd use division. I would end up with like p divided by all of this, right? And so that's not going to help us to get the p by itself. I'll give you a hint. It's really, really simple at this point. So think about what we have on both sides right now and what we might be do if I'm trying to get p by itself. Okay, almost. We are going to drop the log. It's not division, right? Because this is not saying log times p. This is the log of p, right? But because we have a base 10 log on this side and we have a base 10 log on this side, the stuff inside those logs is also going to have to be equal to make these things equal to each other, right? So as long as you've got the same base on both sides here, we can just drop those logs. And so my equation now just becomes p equals p sub 0 divided by t plus 1 to the c power. Now, technically, what we just did there is exactly what German said before, is take the inverse. So we're basically saying, well, if I take 10 to this power and 10 to that power, those cancel, and I'm just left with what was inside the logs. But again, just keep in mind, if you have the same log on both sides, then you're allowed to just drop the logs because the stuff inside the logs has to be equal at that point. Now, all I want to know is, if I were to score a 90 the first time I take a test, I want to know after 2 months, what would I expect to actually score on that test? How am I going to do that now? Okay, so you got 2 plus 1 to the 0.2. That's going to be the denominator, right? Because give us a c value of 0.2, so that's going to go in place of the exponent. The time is 2 months, so that's going to become a 2, right? What's going to go in our numerator this time? Good. So the initial test score that we got was a 90. So that's the p sub 0. So we're going to put 90 up here in the numerator. And we're looking for p because we want to know what would be our new score if we were to wait 2 months. So now we're going to take this, we're going to put it in the calculator. Just make sure when you do this, everything in the denominator needs to go together in parentheses. So if we do that work there, what do we get? You can just round to the nearest whole number here because we're looking for a test score. $72. Good. Right? And if we think about it, let's make sure our answer makes sense. We made a 90 the first time we took the test. We waited 2 months, right? And we took the test again without reviewing or anything else. So it makes sense that we would score lower the second time around, right? So we went from having an A the first time to a C the second time, okay, just because we forget stuff, right? If we don't actually go back and review it. Any questions on that? All right, so we'll stop there. Again, enjoy your 5-day weekend. I will see you on Wednesday, and then the homework will be due Wednesday night by midnight. Okay, so let me know if you've got any questions. I will be working Friday and Tuesday. If you need to set up a meeting with me or anything, just let me know. Otherwise, have a good long weekend, and I will see you on Wednesday.